participants number growing, but I think it's time to start. But before we start, I would like to acknowledge the Ngunnawal people that are traditional custodians of the land of Canberra. I would like also to pay my respect to the elders, both past, present, and emerging. And today we have a very special ACEAS seminar, which is debriefing about the Denman Terrestrial Campaign earlier this year. So now I would like to hand over to Duanne for this exciting seminar.
Thank you, Yuha. Yeah, so I have the joy of reporting on what for us was quite a successful season. And so we'll run through the details of that, I guess of an overview for the first half of the talk, and then hand over to some of the other people that we had out there with us, particularly ACEAS, so Shyla, Mareen, and Cotty, who will detail some of the work that they completed when they're out in the field. So first, a bit of context about the campaign. Why did we choose to go here? Well, it's a reasonably interesting area of the Antarctic Ice Sheet, particularly the East Antarctic Ice Sheet. So it's the northernmost ice shelf around the East Antarctic margin, and it has some fairly unique behaviour in terms of some of the highest rates of sub-ice shelf melt that we see at the grounding line around the East Antarctic margin. And so there's questions around how that's possible and what the drivers are, and whether that's related to some of the high subglacial melt rates that have been predicted underneath the very deep Denman trough, and whether this area is potentially a sentinel for change in the region, and one area where you might see rapid rates of deglaciation through grounding line retreat through the very deep trough of the Denman Glacier itself. There's also been a fair bit of activity in terms of ice shelf loss in the region, whether that's the Cosgrove's ice shelf that calved and disappeared in the last couple of years, or retreat and unpinning that we've seen and speed up at the margin of the Scott Glacier. So quite an active area, and one that's had substantive interest in the East Antarctic context. In terms of understanding some of the characteristics of the region, it's important to separate two major components in the area. So there's the relatively rapid flow that we see in the Scott and Denman glaciers, and also the quite rapid flow that we see along the Denman tongue and the Scott tongue. And that contrasts to the more, I guess, coastal behaviour that we see in other parts of the system, where the ice shelf itself is a lot more influenced by accumulation on the shelf itself, rather than ice that's coming from the deep interior. So we expect that there are differences in behaviour of those two different components of the system, and one of the aspects of the program was to investigate how those things may differ. The overall goals of the ACEAS component of the program were really to look at what the risk of ice mass loss from this subglacial basin is over the next decades to centuries. And we broke that down into four main work packages. So looking at surface mass balance, basal melt, boundary conditions, and paleo environment. And often people contributing into multiple parts of that during the summer. And I'll come back to how well we did against those different metrics towards the back end of the talk. So also worth realising that the ACEAS component was one component of the overall Denman Terrestrial Campaign, and also the broader part of the work that was going into the region. So as I described before we went out there in the November workshop, we had colleagues from SAFE and AAPP out there with us, contributing to the 27 scientists that were within the Denman Terrestrial Campaign, and also the other workers in the region from our German colleagues on the EASY cruises throughout the summer, and looking forward to other work that we've done in the region during the Denman voyage in the following summer. So our work, which here is described in red, really was designed to contribute to that larger understanding of the system. I guess the logistics and the scope of what we were provided with and what we had planned to do. So our major hub, as I had previously described, was located at Edgeworth David. And this was where basically all of our stuff and most of our people ended up throughout the summer. So to give you a bit of an overview of what that looked like. So previously there had been a small field station with 4 or 5 apples and melons sitting in this area. That was supplemented last year by another 4 larger melons that were built, and combined with a couple of the larger tents here formed the major, I guess, working and hub of the station, or effectively the inland station. We had upwards of 35 tents scattered across the other component here, where most people were sleeping throughout the system, throughout the summer, and an awful lot of cargo and science gear that you can see down here on the ice. So this is an epishelf lake, so basically a lake that rises and falls with the tide. You can see the tide crack around the margin there, and provides a nice stable piece of flat ice that is great for landing fixed wing planes on. So all of the stuff that you see here, except for the helicopter itself, flew in with the 2 Baselers that have been shuttling fuel and equipment both this year and last, and provided a really major logistics link that we had back to Casey through the season. So that's where most of the action happened. And for those that were out there, I think you'd agree that at times this really did feel like we were living in an airport throughout the summer. However, not everyone was stationed there for the entire summer. There were 5 satellite camps that the ACEAS team moved around with during the summer for more focused activity, including the larger drilling exercises of the inland raid campaign through drilling into the ice sheet, or the hot water drilling campaign, drilling through the ice shelf and into the cavity below, and other more, I guess, ice marginal camps in the Obrachev or Bunga Hills and out on Mill Island, where we typically have 3 to 6 people rotating through those camps for a week or upwards of a month, depending on which one of those it was. But it was the work that we actually did throughout the season, supported by both those fixed wing aircraft and the helicopters, was obviously much more broad-based throughout the region, and we really did get across most of the areas that we had hoped to go to in the lead up of for the season. So I guess I'd break it down into a couple of different sorts of observations. The geophysical observations in the red dots there, or the more geological ones, the blue dots, and these were largely clustered into 2 different areas. 3 different areas, one of which was more along the grounding line of the Shackleton Glacier and the Scott and Denman tongues. A focused area of activity along the Denman transect, which Shyla and colleagues will talk about later, and the more scattered inland areas of geophysical observations that Coddy will describe, looking at the deeper parts of the ice sheet. And this, I think, has been by far and away the largest and most complex piece of logistics that I've seen the AAD deliver in the 20 odd years that I've been following the program, and potentially ever, in terms of the in terms of the combination of the breadth of scope and places that we were going to, plus the amount of gear and equipment that we were shuttling around, and what were really large scale programs that in some seasons, like the raid campaign or the hot water drilling campaign, would have taken up most of the AAD logistics from a station throughout the season. So I think it really is a testament to the people involved that this was the success was that it was. And as part of that, I think now is a really good opportunity to thank all of those folks ahead of the detail, because there was an awful lot of goodwill from an awful lot of people that made this successful. So we had many things thrown at us in terms of the usual Antarctic factors, whether they be weather or helicopter breakdowns or go slows associated with medical issues on different parts of the stations, that had there not been an awful lot of goodwill and intent from a very large number of people involved in the program, both out in the Bunga Hills during the season, but also before and after, to get our equipment to where it needed to be, and push through the difficulties of losing potentially 3 or 4 weeks throughout different components of the season, but working around those in a way that was really focused on the science and really productive. So I'm very grateful to everyone there, not least of which includes the expeditioning scientists that we had out there with us, that were exceptionally collaborative throughout the season. And there was collaboration between SAFE and ACEAS and AAPP, with people exchanging across the different programs and helping everyone out when it was everyone's turn to have the logistics as we went through. So I'm very thankful for everyone's goodwill there, and just the general level of support that were provided across the summer. So moving into the detail of what we achieved, I'll run through the components that I was most involved with first, and then leave you with some snapshots of things that have either been presented in other forums or forums to be, and then hand you over to the other guys at the back end. So the first component that we'll talk about here is the surface mass balance, and this one is very much a collaboration with APP, with James Newlands, who did an awful lot of work to put out the GNSS towers, which are providing high resolution observations of surface mass balance across the ice shelf at a site up on the ice sheet margin, to looking at how those temperature changes across a year. And we supplemented those, so we, by myself and Lou, through with guidance from Ian Goodwin prior to the season, with a series of traverses across the ice sheet margin, where we're looking at observations of surface melt and patterns of redistribution of snow, both in space and time, across the ice sheet margin, where the catabatics have generated a blue ice area and contributing to melt and runoff. And I guess one of the highlights of me from this part of the campaign so far is the observation of subsurface melt on that margin, which wasn't and isn't being picked up by some of those broader scale satellite-based observations of the region, and I think is something of particular interest going into the future. And the work that we did this summer will contribute to effectively a typology of those different drainage patterns and where and when they occur, at least on this particular margin going forward. One of the other bigger and perhaps in some ways, well, not surprising, but certainly pleasing successes of the season was the drilling through the Shackleton ice shelf to the western side of the Denman Glacier tongue, where I would say a relatively new set of ice shelf drillers, but at least drilling into a cavity of Sarah Thompson and Katie Miles, combined with myself and Maddie Rosevier, were out on the shelf for an extended period, and with effectively a brand new system that had been modelled on some of the gear from our Brunswick, but it was its first use in anger, got through the shelf and were able to deploy sampling and measuring equipment into the water column below. And one of the particular highlights there was, and which has been described previously by a presentation by Sarah and Maddie in one of the other forums, where we picked up effectively modified circumpolar deep water coming in at the bottom of the cavity in this area, and collected sediment cores that should allow us to discriminate whether or not that's been occurring, or that's a recent thing, or whether it's been occurring across much longer timeframes, and understanding how that could be contributing to the subshelf melt that we're seeing both at the grounding line and in areas where that are being measured using AP-RES by AAPP. So I'll also like to mention the work that Ben did to help put that, and particularly by Ben and Sarah, putting that system together ahead of the season to help us achieve that success. The one thing that we missed with that one was the deployment of the mooring, which just proved to be a little bit of a bridge too far with the time and the gear that we had available to us. But we were also fortunate enough to discover through some work around the margin of the Scott Glacier, and particularly just to the west of the Scott Tongue in the Obruchev Hills here, where there's effectively a piece of epishelf lake ice that goes, and an epishelf lake that we're able to dangle C2D down into the ice shelf cavity, and measure the characteristics of the water column that were coming out of that. So this is quite as you can see, with a relatively lightweight field camp that we had there with us on that day, which happened to be the last day of the field campaign. Get quite a useful set of observations, but also an opportunity for relatively easy logistics operation to put in a mooring in what's quite an interesting area in that, and that is something that we're hopeful of pushing forward into the future. The other component that I worked on in detail was looking at the paleo-environmental characteristics of the ice sheet margins in the area, using a combination of different exposure dating techniques, both on the more traditional approaches on the margin, so on the ice-free areas, but also examining characteristics of the margin, be that using the cosmodynamic techniques of the erratics on the margin, or the sediments that have been dragged up by the ice sheet, combined with radar observations, ground-based radar observations of the glaciotectonic structure at that margin, to try and understand how the stability or otherwise of those systems. And with some other indirect measurements based on sediments that have been deposited in epishelf lakes, so basically lakes that sit at the margin of the ice shelf, and the relative sea level observations that are you can make associated with those lakes, to look at how different components of the system may have behaved in the past. And the preliminary data that we have coming out of that, based on the weathering observations and the amount of sediment that's been accumulated at those margins, is that there does seem to be a difference in stability between more terrestrial-based and terminating margin at the edge of the Bunga Hills versus these more active systems in the Denman Glacier and the Scott Glacier and the Obruchev Hills in this area, which were much, much fresher and more recent. So if I was to put a number on it, we're looking at, if not hundreds, then a couple of thousand years of re-advance of the ice sheet in this region from a potential deglaciation earlier in the Holocene inland of the present day, which we should be able to put more constraints on into the future as we go through those dating programs. So I think that's an exciting outcome of the more geological focus programs on those ice margins. The other thing which really was a new component for the Australian program was the rapid access isotope drilling that was conducted by Neroli and Sarah and a cast of 1,000 helpers across the summer, where they're able to drill through several hundred meters of ice on the inland area and collect many ice chips for isotope measurements to work for paleoclimate reconstructions, using what's a relatively lightweight system in that area, and it is again a model for work going forward. And Neroli was able to get a record both inland in terms of more traditional paleoclimate record, something that was similar to, I guess, some of the other programs that have been done in the region, like Mount Brown and Loesing, but obviously focused on the Denman, but also to top up the coastal record that had been completed in the area in the mid-2000s, and collect the ice that had been deposited in that area since then, which, as you can see, is a relatively large amount of ice, and that was, I guess, also demonstrated by the inclement weather conditions that those guys experienced when they were out on Mill Island, which is a small ice dome very close to the edge of the shelf. And hopefully we'll see presentations from those guys on the detail of that going forward. The other aspect that we're expecting to see further presentations going forward is some of the solid earth properties and the deep time history that were conducted by Jackie and Jack, where they were able to get out for more geological focused activities, looking at the materials that are present in different components, and the history of how those things have been put together, and therefore where they might be present underneath the ice sheet, in terms of the understanding some of the deep earth properties that affect the ice sheet, such as heat flow and sediment generation, but also as a proxy for understanding some of the detrital sediment records that have been produced out on the and collected out on the continental shelf break out in this part of the system, either through EASY 2 and 3 or through the Denman Mareen voyage going forward. So again, looking forward to reporting from those guys into the future. So that's a really good point for me to segue across to the first of our ACEAS, which is Shyla, who's going to report on the seismic applications that were focused on understanding the characteristics of the ice sheet and the deep earth properties in the area. So Shyla, I'll let you take that away.
Thank you, Duanne, for the introduction. Again, my name is Shyla Kupis. I'm an ACEAS PhD candidate at the University of Tasmania, and I had the wonderful opportunity to partake in the Denman Terrestrial Campaign this past season, along with my co-supervisor, Dr. Tobias Stahl. I will be speaking on behalf of my team, which is the ACEAS Grit Seismic Field Team, and just briefly discussing our objectives and outcomes from this past Australian Antarctic field season. Next slide, please. All right, so here is a map to give you an overview of our GRIT seismic deployments. So GRIT is geophysical research infrastructure in Antarctica, and that was supporting the instrumentation that we were able to deploy in DTC. So there are 3 types of seismic deployments we had. We had long-term monitoring stations, which is that bigger green triangle, and you can see that located in the Bunker Hills region where that exposed rock outcrop is. This is equipped with GNSS system that's been there for over 20 years, and also a seismometer that's been there since 2016. This requires routine monitoring, offloading data, and upkeep. In addition to that, we deployed our overwintering passive seismic stations. We had 11 in total, and these were deployed along the Denman Glacier flanks and around the margins. And if you look down a bit south, we have our short-term passive seismic stations. This is part of a multifaceted study to look at inland of Denman Glacier. There was modeling to show that it is the deepest inland trough in the world. And as Denman Glacier has the potential to contribute about 1.5 meters of sea level rise, it's really imperative for us to have a better understanding of how this will influence ice flow. So before I end with that, I just want to mention for our overwintering passive seismic stations, these are part of a greater study to look at receiver functions, to look at deep earth properties in East Antarctica, which has typically been quite sparse. So we're trying to get a better picture in this region in East Antarctica. So next slide, please. All right, so there's 2-fold applications to our seismic. The first being passive seismic. So passive seismic uses Ambient sources of noise. So these are low frequency events. You can look at teleseismic events, which are earthquakes that you can pick up 1,000 kilometers or more from their source. You can look at ice quakes. We also wanted to see if we could use the ice drill as it's drilling and penetrating into the ice sheet as a potential seismic signal as well. We had two types of instrumentation. We had broadband seismometers, which look at a wide range of frequencies, and we also had geophones. For the passive seismic, we had short-term deployments and overwintering stations. These were co-located with the magnetotolarg stations in the Antarctic Plateau along the Denman Glacier transect, and also at the ice drill sites that are part of the RAID campaign. And you can see some nice photos of us in action, doing some seismic work at the RAID 1 and 2 drill sites, and also our seismic stations and some of the setup. Next slide, please. All right, so I was able to be a part of both of the RAID campaigns, so RAID 1 and RAID 2. RAID 1 is located inland in the East Antarctic Plateau. Again, this is looking at a paleoclimate record from ice chips that are sampled from an ice drill. And prior to my arrival, Dr. Sarah Jackson and Early Abram, they deployed the passive seismic array, which you can see illustrated in the top figure. And this is in line with the drill. And then upon arriving, then I was able to deploy a hammer refraction survey both to the east and the west in line of the drill. And then moving on later in the season, there was a second RAID campaign at Mill Island, which you can kind of see located on the map. And here again, this was a passive seismic array and also hammer reflection surveys. And it was quite exciting with the hammer reflection survey because it coincidentally ended up being co-located with the most recent airborne radar flight line from IceCap. And that was just a day after I had finished up the hammer reflection survey. So that'll be interesting to have for comparative purposes. Next slide, please. All right, and so the second component of our passive seismic deployments is the overwintering stations, part of the GRIT program, and these are again for part of that larger receiver function array. And what we're interested in looking at is understanding the foundations and the structure of the Denman Glacier flanks. So looking kind of at like the basal topography and what kind of layering or structures we can see. And then we also want to monitor the feedback from the solid earth as it responds to ice changes. So you can have uplift as you have ice mass loss, or you can even have uplift and then deformation as you have more ice layering on to the solid earth. So we want to study this using our seismic stations. And here you can see Tobias and I just setting up. Oh, yeah, that's okay. Here is Tobias and I were just out deploying a few of our overwinter sites. So we have the solar panels rigged up to keep our station running and recording data. And this is around the Denman Glacier and Cape Horsley and Cape Jones. Next slide, please. All right, and so the second component to the seismic applications is active seismic. So active being you have an active source. This could be from explosives. In our case, we were hammering a metal plate to produce our seismic signals for our geophones to pick up. So this was exciting because I got to work very closely with a new type of instrumentation called Smart Solo geophones. And these were the first time in the first season that GRIT has deployed these out. And this is part of a larger discovery-driven research endeavor. So we want to use this instrumentation and observe what kind of data quality that we can receive from it and what kind of features that we can resolve from the data we have. So some features of interest are looking at the ice bedrock interface, moraine extent, or gradational changes in the ice and fern layering. So there are multiple locations. We had, again, as aforementioned, the RAID 1 and RAID 2 campaigns. We had hammer refraction and reflection surveys. And then we also conducted hammer reflection surveys along the epishelf lake called Transcripti Bay. And just in case you aren't familiar with an epishelf lake, it's just a lake that fluctuates with the tide. And usually it kind of buttresses an ice shelf from the fresh meltwater from glaciers. So this was an exciting collaborative opportunity to have our hammer reflection survey in tandem to NMT station, some GPR, ground-based GPR, gravimetry, and some borehole measurements. So those are some of the pictures you can see here. And then if you look to the right-hand side, you can see we also had active seismic deployed along the Denman Glacier transect. And if you don't mind, can you play the video, Duanne? You can see Toby in action hammering. So yeah, you can get an idea of the kind of work that's involved. All right, that's great. So next slide, please. All right, so that was just a brief overview of our seismic field objectives and outcomes from this field season. But currently our seismic data processing is underway, and we really look forward to sharing our results with you in the near future. In the meantime, please do not hesitate to reach out and get into contact with us. I've included our contact information for the ACEAS Grit Seismic Field Team. And yes, with that, I would just like to thank you for listening and hand this over to Koti to talk about her research in magnetotellurics.
Thanks, Shyla. Well, hello, everyone. So I'm Koti Manassero, postdoc at UTAS, working with Kate Selway and Anya Ridan, and also part of the GRID project. So yeah, as I mentioned, some of us were doing geophysics, and with geophysics like gravity and seismic, as Shyla was explaining, we are taking measurements on the surface and looking beneath the surface, right? So this way, we can look through the ice and the rocks beneath, and we can go quite deep into the earth, right? So Kate Selway and I were collecting magnetotelluric data. And for those who don't know, because it's not a well-known technique, MT is a passive technique that measures natural variation of Earth electric and magnetic fields to determine electrical conductivity distribution below the surface. And again, it can go quite deep, like up to like lower mantle. So since the conductivity depends on the composition, temperature, water content, and salinity, with MT we can identify, for example, the base of a glacier, subglacial water, water content, and temperature in the mantle. And the longer we leave the instruments recording, the deeper we see, right? So next slide, please. And here's a time lapse. I think you can play it. Explain. Yeah, so this is a time lapse of an empty installation on the transect, on the Denman transect, that illustrates a joint effort that it takes, an amount of hours. It takes, yeah, around 3.5 hours. To collect our data, we bury these like long red tubes that are called magnetometers that actually measure the magnetic field. And then at further locations, we put 4 metal sheets that are called electrodes. So these electrodes are acting like big voltmeters at the surface, and they are measuring the difference in voltage between them. So with this whole setup, we are basically measuring the electric currents and magnetic fields that are naturally occurring in the Earth. And from that, we can see which parts of the Earth are more conductive, right? So next slide, please. And there's another video too of the Denman there. Yeah. So the most challenging project that we had was the transect on the glacier. And this was because it was extremely crevasse, as you can see on the video there. So there was a lot of work done by the FTOs and the pilots to make sure they clear the site. You can see some of the photos there from the air of the FTOs on the site clear the site. And also the main thing that we had was dealing with the wind, right? We could have like up to 25, 30 knots winds. And even though these photos are from a beautiful day, it was very hard to work in those conditions. So it was a lot of, a huge amount of effort from the whole camp and from everyone involved to send us there, right? Next slide, please. And there was also a lot of effort when digging out the instruments, because mainly when we had high accumulation areas, so the pilots and FTOs were digging a lot. Yeah, it was a very joint effort and very successful in the end, but it took effort, right? So next slide, please. Just a video showing some sites on the plateau. Yeah. So here's a map of the MT stations that we deploy so far. In black and white, we have the sites that we collected this year, where the black spots is a set of data widely spaced over the plateau. And in white, we have the sites over the transect. There are 5 sites. We also have some data that were collected last year in orange. So with these data sets, we have 2 different goals. Next slide, please. So the data from the widely spaced sites will be used to obtain information about the viscosity of the mantle beneath Antarctica from the conductivity models that we obtain. So this is an example of the information that we can get from the data from the sites on the plateau. So on the left, we have the mantle conductivity model down to 400 kilometers into the Earth. And this is from data that Kate collected in Svalbard. And this is showing how conductive the surface is, right? So we have in red and orange more conductive areas, and then in blue parts more resistive. So essentially we can turn these models into information of mantle viscosity, and this is super important to improve the GIM models, right? So mainly because when we model how much ice is being lost, we can see how much the ice surface is going down with GNSS, but we don't know how much the Earth is going up, right? So we need information about the mantle viscosity. So in the panels in the middle, we actually have 2 different models of the uplift rate, and the one on the left is generated with a 1D Earth model of viscosity, and the one on the right includes 3 lateral changes, a 3D lateral change in viscosity. So we can see how different those models are and how important it is to have the information of mantle viscosity overall. One of the most important things too is having seismic and MT data together as collocated data, as Shyla was explaining, because then this helps putting better constraints on the temperature and viscosity models. And so it's great that most of the data that we have are collocated with seismic too. Next slide, please. So with data obtained over the Denman Glacier, we aim at looking at shallow depth, particularly the base of the glacier and any meltwater that we could have there. So as Wayne was mentioning before, Denman Glacier has been modeled as being the deepest trough on Earth, like around 3.5 to 4 kilometers deep. And if it's as deep, it has a big potential to contribute to sea level rise. But this trough has been modeled so far with airborne data. So the main objective for all of us was to go there and collect gravity, seismic, and MT on the surface and see how deep Denman Glacier actually is, right? So before we get the results, we need to process a lot of data that I'm gonna touch a little bit on that later. What is doing what I'm doing at the moment. But here on the left side, we have kind of the results that we are expecting to see. So the ice will be this resistive layer of blue on top of the bedrock, and we expect to see some conductive layers, which mean meltwater. And then again, we will use this information in combination with some of the gravity and seismic data to have a better understanding of how deep the glacier is and constrain the models itself. Next slide, please. So the first step in the data processing is a visual inspection of the time series to identify noisy sections mainly. A big source of noise is the wind and storms, as everyone has mentioned. We have a lot of winds there, so the wind creates and the moving of snow creates static charges that produce localized electric fields and affect all our data, right? Masking the structures that we could see. So the main thing that we need to do is go in frequency by frequency and clean the data, right? So next slide, please. So this is an example, for example, of the noisy raw data on top and then clean processed data at the bottom. Next slide. So when we have the processed data, what we do is a dimensionality analysis, and this involves computing and plotting different values as ellipses to analyze if the data behaves as a 1D, 2D, or 3D. And this will also determine which type of technique, modeling we will apply to obtain the conductivity models in the end, right? If it's 1D, 2D, or 3D. So we do this analysis per frequency or period, which is the same. So shorter periods reflect shallow depth, right? And this plot then shows the data for the 5 stations over the transect for different periods, right? So where the ellipses are more circular, it indicates a 1D environment, as we see on the top left on the shorter period, which indicates, in this case, the ice. And the deeper we go, the ellipses become more elongated, indicating 2D or 3D structures, no? So a more complex structure. So this is very important to, again, identify which methodology we're going to apply. We can also see that the orientation of these, the major axis of the ellipses, which give us the orientation of the current flow direction. And also this is very, very important to give us an overall view of what we are seeing. And we also have, those arrows are called induction arrows that are ratios between the vertical and horizontal magnetic fields and are used to infer lateral variations in the conductivity, right? So if you see all of the arrows point towards the east of the glacier, which coincides with the what we saw, like the higher speeds. So far we know that there's most likely a big conductor underneath there, and it could potentially be linked with those higher speeds on the glacier. Next slide, please. So yeah, at the moment we are finishing processing the data and starting to produce models, but yeah, stay tuned for the results. And as Shyla was saying, we are MT team, Kate Selwyn and I, and if you are interested or have any questions, suggestions, just send us an email. Thank you very much. And yeah, now I think it's Mareen's turn. So she will talk about gravity.
Yes, thank you, Coty. Hello, everyone. I'm Mareen, and I'm an ACEAS funded postdoc at the University of Western Australia in Perth, under the supervision of Alan Aitken, who did very much all the planning of this part of the project. And I had the great opportunity to join the Denman Glacier campaign to measure the gravity and some rock properties. Next slide, please. So the main goal of our project was to improve our knowledge of the Denman Glacier trough geometry. And radar data, as shown in the red plot as these black crosses, fails to probe such a deep subglacial trough due to the steep valley walls that yield like side reflections. And so we don't have very good constraints on the actual depth. And previous maps like BATMAP2, shown here in green, and BATMachine in blue provided some estimates of its depth, either by kriging interpolation or mass conservation technique. Unfortunately, exactly these areas are critical because they control most of the ice discharge in Antarctica, and the resolution required by ice sheet models is typically at least 1 kilometer. So we need the small scale details to better understand the changes in the glacier flow to project ice sheet evolution into the future. So because the assumptions made in the mass conservation method and the uncertainties of the input data, we still lack the detail and certainty, and we need to integrate more data sources to better quantify the subglacial topography. Next slide, please. So gravity measurements can significantly help because they are influenced by mass distribution of both the ice sheet and the underlying bedrock, and can therefore contribute to understanding the topography. And so we went to a spot on the Denman Glacier. Can you go to the next slide? Yeah, I had some animations in there. Yeah, where there was already an airborne campaign that flew over, taking airborne gravity, magnetic, and radar data. And so we went there to complement these data with higher resolution ground-based data. In total, I took gravity measurements at 9 different sites there that have been cleared by the AAD along a profile of about 16 kilometers in distance. And next slide. Next slide. Yes. So this was the setup from above. Because it was about 100 kilometers away from the camp, we had to fly there with 2 helicopters, one for me and 2 FTOs. They had to clear every site to make sure that there are no hidden crevasses, like Cody already explained. And then the 2 other teams, so Cody and Shyla's teams, could go with the other helicopter and fly to the sites that were already cleared. Next slide. Yeah, so flying over the glacier already showed us how dynamic it is and how crevassed it is in some places. And yeah, it flows with almost 2 meters per day, so can be a very dangerous endeavor. But next slide, please. Yeah, so I have 2 videos. Yeah, so the routine was that when we land, one of the FTOs gets out. The person is roped to the helicopter and then probes the subsurface with a stick to see if there are any crevasses. And if it's clear, then we could jump out and take the gravity measurements. And then the FTOs, both of them, get further out and clear the sites for the other groups that need a bit more of space. And can you start the next video? Thanks. And then, yeah, working on the glacier, as Cody already explained, is quite tricky. It's not only requiring a fast routine, but also very difficult with strong winds up to 40 knots, I think, and drifting snow. So yeah, that was quite of a challenge. Next slide, please. So because of that, and because of the gravimeter that is quite sensitive, I conducted the gravity measurements under the BB bag, which you can see in the right picture. And yeah, on the left, you can also see the GPS measurements that I need to take on every side to measure the height and the position. Yeah, and that's sort of the setup at every site. Can you go to the next slide, please? So the measurements that I got from the 9 sites are then shown here as the dots. And compared to the airborne data shown as a solid line, they indicate that the trough can be could be quite steep and also quite deep. Next slide, please. So now in order to estimate the depth, I did some simple 2D profiling, or 2D profiles with constant densities for the bedrock and the ice to model the possible topography setups. So in this one, the trough could be even as deep as 6 kilometers. But next slide, please. Changing the geometry slightly and slightly ignoring one of the points on the left. Sorry, can you hear me correct? Okay.
It's a little bit weird.
Okay. I'll just continue if that's okay. I don't know.
No, I think it's better. Yeah.
Okay. Yeah, so in the second plot, I changed the geometry slightly and ignored one point a little bit. And then, yeah, we can model a completely different geometry. And if you go to the next slide, we can also include dense sediments, for example, at the bottom with less dense infill. So yeah, all of these models so far indicate the trough that is deeper than 3.5 kilometers, as suggested by Bed Machine. If you go one slide next, yeah. But of course, this is a very simple model, and we don't take into account any lateral density variations. And also it shows how variable these interpretations can be without any further constraints. So having seismics and MT data alongside the gravity is really valuable. Okay, next slide, please. So further, I'm going to work with Mickey and the Gator Glaciology group from Florida to model the trough and its surroundings with a probabilistic 3D approach. So this, in contrast to classic kriging interpolations, creates many different randomly created but more realistic topography realizations, and then estimates their ensemble mean and uncertainty. So this is very much work in progress and still needs to be refined, but that's just how to show you the overall idea of what I'm going to do with the data. Next slide. As a secondary project, I had the chance to accompany the two geologists, so Jackie Halpin and Jack Mulder. So I could take gamma ray intensity measurements, which give me an estimate of the prevailing heat production of the rocks. And next slide, please. And I could take additionally some susceptibility measurements, which indicate magnetization of the rocks. Next slide, please. And then in total, I took measurements at 183 rocks at several different outcrops around the Bunger Hills. And additionally, on some bad weather days, or when other groups were out with helicopters, we took some ground-based magnetic data. Next slide, please. Yeah, by hiking across the Bunger Hills, and they already sort of indicate a good correlation to the already mapped geological units. So that's great. And it was an overall very successful campaign, and the measurements are also very valuable for my work. So next slide. So this is to give you a brief insight. I'm working on using gravity and magnetic data with machine learning to link them to the measured information. And so with the collected data, but also with some additional data from Australia in this case, I'm trying to predict a regional heat production and lithology map of Antarctica. So the more data, the better these maps get, and the better we can understand the basal conditions of the Antarctic ice sheet. And yeah, if you have any questions, please feel free to ask or contact me later. That's all for me. Thank you.
Well, thank you, Duanne, Shyla, Coty, and Marie for the exciting results. And if you have any questions, now it's time. So would you please just raise your hand so I can unmute you? Yeah, go ahead, please.
Hi, that was a fantastic presentation. Thank you very much to everyone. Just for Mareen, do your results mean that the Denman Glacier is larger than previously modelled? Is that what your interim results show?
Well, yes, the simple 2D models show that it could be deeper than we previously thought. Yes.
Matt, please.
Yeah, thanks, Yuhao. And thanks everyone. Great presentation. Sorry, I should turn my camera on. Yeah, wonderful stuff. Duanne, I wonder if you could say something, or maybe the others want to say something about how you hope to link that sediment core that you got under the Shackleton with what you're finding upstream in terms of the geology, and if there's a plan in linking those together.
Thanks, Matt, and sorry, my video seems to have died. Yeah, there certainly is opportunity to look at the detrital characteristics of the sediment within that core, basically to see where the glacier has been eroding at different times, and see whether different time periods producing different effectively type or different source areas for the rocks, which would give us an indication of changes in particularly the erosive behaviour of the glacier, which are strongly related to the grounding line. So the sediment core that we have underneath the ice shelf is likely to give us upwards of a few thousand years in terms of history. But I think some of the real potential for understanding change is where that sediment is then going further out onto the continental slope, and where there's likely to be much longer term records. And so we could look at time periods such as the last interglacial or some of the other Pleistocene interglacials, and looking at warmer periods and seeing, you know, basically where the ice sheet margin may have been during those times, and how much ice loss we might have had out of that system.
Nathan has a question, and he has already put it in the chat. So what does the depth of the Denman Glacier mean for the upstream basins or past volume of the catchment volume?
Why so deep?
I'm not sure if I should answer that question. I think generally deeper trough is more prone, or makes the glacier more prone to the marine ash instability. But I'm not quite sure what that means for the past volume of the catchment. I'm not sure if Duanne wants to talk about that.
I think in terms of the past behaviour, it's probably more a function of the longer term evolution of the system, and especially the tectonic characteristics of that area. So it's quite likely that, given we have a very deep trough, if it's anything like some of the other regions like the Amery, where there's like Permian sediments present underneath those systems, it's probably a function that area was a previous river valley basin or a rift basin heading into the glacial period, and that the glaciers basically exploited that. And Jackie's probably even a better person to ask on that than me. So if she has anything to add, then please do so.
Yeah, thanks, Duanne. I think you answered that well. Like, if you're asking why so deep, Nathan, there's geological complexity under there that we understand it to be an area of weakness in the crust. So there's a sedimentary basin sitting under the Denman region that contains rather less rigid, more weak rocks than the surrounding areas. And there's also some very steep bounding faults that have been active in the past through that area. So there's a deep geological control on the depth of the Denman Glacier. In terms of what it means for the catchment, in terms of Mareen and Crotty and others' new data in terms of the depth of the trough, I think that's to be realised once the modeling's complete as to what impact that might have on the sort of catchment area.
Thank you. Thank you very much.
If we don't have further questions, let's thank our speakers again for these nice presentations. And see you at the next ACEAS seminar.